Okay, so welcome back from lunch. I'd like to introduce the next talk called Visiting the Bear Den by Joan, Calvet, Jessy, Campos, and Thomas Dupuy from ESED.
Thank you. Okay, so hello everyone. I'm Thomas. I'm a malware researcher at ESET, an IT security company, and I'm here with my two colleagues, Jessy and Joan, to talk about a group of attackers we have been tracking for the past 2 years. So we call this group the Sednit Group, but depending on the researchers, it has others' names like APT28, Fancy Bear, Strontium, Sofacy, etc. The Sednit Group has been doing targeting attacks since at least 2006, and their interest is mainly about geopolitics. So in this presentation, we'll first give some context on the group, then we will present a textbook case of their current operations, during which we will dig into their toolset. After that, Jessy is going to present a different and strange operation also run by the Sednit Group over the last few years. And finally, we will conclude with some lessons learned and open questions. So let's start with some context around Sednit. So what kind of people are they after? For once, we know very precisely some of their targets due to a mistake they made with their phishing campaign. The operators use Bitly to shorten their phishing URLs, but forgot to set the Bitly profile to private. So we had access to around 4,000 shortened URLs during 6 months in 2015. And here is an example of an URL that was shortened. It contains the email address of the target and its names. So yes, in some case it was easy to identify the target. In this list there are embassies and ministries of more than 40 countries. They are mainly NATO and Europe institutions. And finally there are a lot of individuals involved in Eastern Europe politics, like politicians, activists, etc. So to infect those targets, they pull out several zero-day exploits. Here, as you can see, a timeline with the Sednit zero-day exploits used in 2015. Of course, all these vulnerabilities have been patched since then. And here, we are not even talking about revamped exploits they use. There are many of them, as we are going to see. So it's also the kind of group that deployed many custom software over the past 10 years, from droppers to an encryption proxy tool, including different types of backdoors. The thing is, they develop a lot. But before going further, we want to mention a few disclaimers. First, even if we track Sednit closely during the last 2 years, our visibility is, of course, limited, and we are missing parts of the picture. As malware researchers, we call it a group based on their toolkit, but they may be actually divided in sub-teams, of course. And finally, we are not competent to do any attribution, but our research provides hints that may be used for that. So let's start our journey in Sednit toolkit with Serge. So Serge is actually a code name for an imaginary Sednit target. He works for a government and has access to sensitive information. The chain of events and the timings that we are going to present in Serge's attack are in line with several real cases we recently investigated. And we use Serge as a textbook case to present a part of the Sednit toolkit. So somewhere recently, it's Monday, 9:30, our buddy Serge arrives at work, grabs a cup of coffee, and opens an email. So this email supposedly came from Stratfor, which is a so-called an intelligence company, and which provides regular reports on geopolitics. And if we look closely at the URL, we will notice that the domain mimics the legitimate Stratfor domain. But also, the URI is the same as an article on the Stratfor website, except that an ID was inserted in the middle, probably to identify the target. So Serge clicks on the URL and meets Sedkit. Sedkit is a Sednit exploits kit. It's used only for targeted attacks. As we just saw, its entry point URLs mimic legitimate URLs. The exploit kit infections usually start from targeted phishing emails, but we also seen iframe redirections to Sedkit from hacked websites. And we found Sedkit in September of 2014 for the first time, and is still in use. So as a classic exploit kit, when you visit it, you receive a landing page that will build a Reconnaissance report on the machine. The Sedkit landing page contains around 200 lines of JavaScript, and the code stays the same over the last year. You can see a beautified extract of this landing page. First, it retrieves the time zone. Second, it enumerates the properties of a JavaScript object called navigator and screen, which provides information on the browser and on the user screen. And finally, it enumerates the plugin installed in the browser. As you can see, there is a special case for Internet Explorer where Java and Flash are detected by special methods. And just to mention, the comments here are from the developer. So to give you an idea, here's a report from Serge's computer. It's a JSON representation. So you can see it contains a lot of information such that the server can select the targets very precisely, not only on their config, but also on the language they speak or the time zone they are in. However, we don't know very precisely what the operators are looking for. We crawled the exploit kit with various configuration and different IP addresses. Sometimes it works, sometimes it doesn't. And right now, we don't know really why. So let's say that Serge is selected to be exploited and visits the Sednit exploit factory. Here's a list of exploits that we saw from Sedkit since its beginning. As you can see, 3 of them were zero-day exploits at the time they were used. Interestingly, there is an exploit for MacKeeper, which is a cleaning tool for OS X made by a company from Ukraine, and probably used mainly by people from Eastern Europe. And the other exploits are revamped exploits, and we are going to describe one of them that we recently found, which is not documented as far as we know, while the zero-day exploits have been well described by other researchers. So this exploit targets the CV 2014-6332. This vulnerability is an integer overflow in Internet VBScript engine, and it allows arbitrary read and write in memory. We saw Sedkit delivers this exploit for the CV in October 2015 for the first time, and in this case, it just reuse a public proof of concept to disable the safe mode and download the next stage binary with PowerShell. But recently we found a very different version of this exploit, more complex. It was used in February 2016, and this exploit didn't disable the safe mode, but directly execute a ROP shellcode. The code is pretty big, around 400 lines of VBScript, and interestingly, it's custom, and we didn't find any similarities on the internet. So here's a beautified code of the function to build the ROP chain, and this chain will be executed thanks to the vulnerability. We are not going to dig into the exploit itself, as we are still analyzing it, but there is something striking here. Indeed, the code contains a lot of helpers function. It actually looks like a framework for exploitation, for exploits in VBScript. And for example, you can see a function to retrieve the code section address of DLL on Windows 7. As you can see, it's a lot of effort, but please do not try to read this. It's VBScript, you know. So to summarize, it looks like an exploitation framework. It smells like an exploitation framework. So we believe it's an exploitation framework. Here are some of the function names. You would expect to find those functions on the internet somewhere, but there is no sign of them. So guys, if you ever seen this, please let us know. So back to Serge's cases. The exploit downloaded on its computer downloads payload, and Serge meets SEDUPLOADER. SEDUPLOADER is usually downloaded by Setkit. This component actually includes two binaries, a dropper and its embedded payload, and it's generally the first component deployed on the victim. We dated the apparition of SEDUPLOADER in March 2015, and it's still in use. So let's start with SEDUPLOADER dropper. As you can see, its workflow quite straightforward, but it contains some interesting features. The first one is a weird anti-analysis trick. Here is a snippet extract from X-rays. So first, it allocates a 10-byte buffer and sets the last byte to the value 42. Second, it creates a temporary file named juguid.temp. Third, the code writes 1 million times in this buffer, in this file, and then reads 1 million times in it. And finally, it checks if the last byte of the 10-byte buffer still contains the value 42. If it's not the case, SEDUPLOADER will terminate its execution. So this code looks strange, and we believe it's a kind of anti-emulation trick. First, it creates intensive hard drive operations that delay the execution, and also it may detect emulators wrongly implementing memory management, which are not able to maintain a 10-byte buffer state due to the amount of read-writes operations. The next step is decrypting the payload and decompressing it. These operations are implementing in a C++ class named Uploader by the developer. And the next part is the juicy one. The dropper uses local privilege escalation exploits. Depending on the sample, one of these two CVs can be exploited. The first one was a 0 day at the time that Sednit used it. And the second one is another gift from Hacking Team Leaks. Finally, the dropper makes the payload persistent on the system. Interestingly, we saw many different techniques used over the past month. Some of them only used when the dropper runs with system privileges. And here you can see just a few of them, like Windows COM object hijacking or JavaScript code executed in RedDLL32. And just to mention that these two techniques were first seen in other malware and then integrated in SEDUPLOADER dropper. So seeking inspiration in crimeware is something usual for the Sednit Group. So at this moment, the payload is running on Serge's computer, and SEDUPLOADER payload, it's a kind of Reconnaissance malware, and you can see here the simplified workflow. So the first part is establishing the network connection with the CNC server. It's probably the most remarkable part of the payload. It's changed several times in the last few months. And the first method is a basic one. It tries to contact a CNC server, and if it works, it just moves on. However, if it doesn't work, it retrieves a proxy credential. For instance, for Firefox, the payload will look for the profile file and parses it. If it succeeds, it will contact the CNC via the proxy using these credentials. And last but not least, if all previous techniques didn't work, it will wait for the user to launch a browser in order to inject in it. The next step is to send a first stage report to the CNC server. This report begins with an ID generated to identify the computer, a process list, disk information, and build number, which is hard-coded in the binary. And then it sends all of it encrypted through the network link that was previously established. And you can see it's a small report, probably to filter out security researchers. The final step is retrieving a config from the CNC server. Here's the different values handled by the last version of SEDUPLOADER payload. I will not pass through them, they are quite explicit. But the main purpose here is to download the specific file from the CNC and execute it as a DLL or an executable. So to conclude, just a quick anecdote. In SEDUPLOADER samples, the return code of each API call is printed into a file. Here's the beginning of this file. That's kind of API execution trace. And each line corresponds to one Windows API call and begins with an acronym indicating which type of API call was logged. So the developer probably used that to debug the code. So why not?
Okay, so now let's get back to our chain of events. We are still day one, and Serge's computer is still infected with SEDUPLOADER. Same day, 30 minutes later, now that the operators are sure our boy Serge is not a malware researcher, SEDRECO is downloaded on Serge's computer by SEDUPLOADER. So SEDRECO is a classic backdoor with numerous commands, and it has the ability to extend its behavior by loading external plugins. And it is usually deployed after a successful infection, like in Serge's case. While this component might be old, we know for a fact that it is still actively used nowadays. So, usually SEDRECO arrives on a computer in a dropper, and it usually installs the payload and its configuration. It will drop the configuration at two different locations on the disk. First, it will write the configuration in a file named MSD, and then it will also write the exact same data in the Windows registry. Since the configuration is installed by the dropper, that means that if you only find the payload, you won't be able to determine which configuration was used with it. So let's talk a little bit about this configuration now. Here you can see the encrypted version, and it comes with a small header, and the data is XORed with a 6-byte key. The key is located in the beginning of the configuration and is randomly generated by the dropper. And following the key, you have 20 bytes, and each byte represents the size of one of the fields in the data. Everything else is the encrypted data. So now here's the content once decrypted, and here is the better representation of the extracted field. So those values are just some various timeouts used by the payload, but I won't describe them because they are not very interesting. Here we have the computer name of Serge. Also, here we have a keylogger flag specifying whether or not the keylogger should be enabled during startup. We have the 3 CNC used with SEDRECO right here. And the first CNC is the main one, while the two others are just fallbacks. Here we have what we believe to be the operation ID. And we have found so far 4 different operation IDs. They are shown on the screen. And here, as I mentioned before, SEDRECO has the ability to load external plugins. So at the end of the configuration, the plugin path will be stored, but they are missing right now because the payload doesn't come with any plugin when dropped. So let's talk about the payload that uses this configuration now. The initial payload usually comes with 26 commands, and each command is identified with a unique number. Those commands are registered by an export called register new command, and here you can see the registration of a few of them. So SEDUPLOADER capabilities are numerous. For example, it can read or write any file on the system. It can list all running processes. Also, it can manipulate the registry. But more interesting, it can also enumerate network resources, the plugged devices. It can update itself, its configuration, or load or unload any plugin. So speaking of plugin, they come as DLL and they will be loaded in the same address space than the payload. And thanks to that, they are able to use any function of the main payload. So as shown on the picture, here is what happened when the payload initializes the plugin. It calls the plugin init export, passing some function addresses to the plugin. And in particular, it will provide the addresses of the function handling the output formatting, like here. And also, it will pass the addresses of the function handling the registration of new commands, so the plugin can register additional commands if needed. And here is an example of a plugin we found used in parallel with SEDUPLOADER. This module was just registering a new command, this time opening an HTTP channel on the infected computer. We can see that not every argument is used, and also we can see what kind of possibilities this kind of plugin mechanism can offer. And also, to finish with that, when SEDUPLOADER is terminating, it will call the init export of the plugin, and this export, in this case, only deregister the command.
So let's go back to a chain of events. We are still day one. SEDUPLOADER was deployed 30 minutes after the initial infection with the exploit kit. Same day, 4 hours later, Serge meets XAGENT, which was downloaded by SEDUPLOADER exactly like SEDUPLOADER. So XAGENT is a modular backdoor written in C++, and for which there exists at least a Windows, a Linux, and an iOS version. XAGENT is really the flagship backdoor of Sednit. They use it in most of their operations, usually after the Reconnaissance phase, like in the case of Serge here, but also sometimes as a first-stage malware. We dated the apparition of XAGENT in November 2012, and it is still in use. So at this point in this presentation, you are going to expect some reverse engineering on C++ binaries, except that, due to a mistake from the operators, we recently got access to the source code of XAGENT. So we are going to do some C++ source code reverse engineering. There is an extract of the files we found. It's a fully working C++ project of the Linux version of XAGENT, and it was compiled in July 2015, which we know because there is a bin folder with a binary from this date inside. The project contains around 18K lines of code in 59 classes, so it's pretty big. And we believe this Linux source code derives from the Windows version of XAGENT, because at several places in the code, the developers commented out some Win32 API calls and replaced them with some Linux-specific API call, like in this case for thread termination. Finally, there are several versions of XAGENT, and the source code is major version 2, while the currently distributed binaries are version 3. But the source code still matches the core logic of the version 3 binaries. As you would expect in such a big project, the source code is heavily commented, and the comments are basically a mix of badly written English with some Russian and some ASCII to describe the data structure. So that being said, let's dig into the code. The logic of XAGENT starts in a function called startXAGENT, located in main.cpp, and you can see here an extract with the main steps. First, an agent kernel object is instantiated. That's the execution manager of XAGENT, the kernel. Second, an iAgent@channel object is instantiated. That's the means of communication with a CNC server. And as you can see, in the project, there are actually two channels, one using the HTTP protocol, called HTTP channel, and one using emails, called mail channel. But as you can see, the developers commented out the mail channel instantiation, even though XAGENT is completely capable to manage both of them at the same time. Third, two iAgent module objects are instantiated, and those modules implement the functionalities of XAGENT. Remote shell provides the shell access to the operators, while FS module is a wrapper for file system operations. And as you can see, the developers commented out the keylogger module instantiation. Then there are some calls to the kernel method register channel and register module. And with that, the kernel starts managing those modules' execution and pass their communication through the registered channel. As you can see, the developers commented out the registration of the left-out channel and module. And finally, there is a call to the kernel method start work, which creates execution threads on each module and channels. So something I would like to point out here is that the strategy of commenting out certain modules and certain channels is something we previously observed in the binaries. Indeed, each XAGENT samples come with a combination of modules and channels specifically chosen for the target. And the developers can actually, later on during the execution, deploy new modules and new channels by sending a specific command to the kernel and the C++ object they want to deploy as a module or as a channel. So you get an idea here about the design behind XAGENT, which is quite elegant. So now let's focus on the communications with the CNC server. Here is a simplified view of the communication workflow. At the center, on the XAGENT infected computer, there is the kernel run method, which is in an infinite loop. And first, it fetches messages from the modules, and notice that the kernel itself is a module. Those messages are unencrypted C++ objects, which are then serialized and encrypted by the kernel, and then given to the channel controller, which is the interface to contact the CNC server. And the channel controller simply forwards the message to the server. In the other direction, the channel controller regularly asks the CNC server for encrypted message for a specific module, and then gives a message to the kernel which unserializes this message and decrypts it, and then gives it to the intended module. So one of the beauty behind this simple design is that the channel controller is completely unaware of the actual channel implementation. And as I said before, it can be over HTTP or over emails. And the channel controller can use both of them transparently. And in fact, it will automatically switch to a different implementation if the currently used one is not working anymore, and if it has the two implementations at its disposal. Speaking of a channel, let's focus on the email channel. How is it working? The workflow is quite simple. When the channel controller has a message for the CNC server, the mail channel sends an email with the message as an attachment to an inbox. And this inbox can be a free mail address, a Sednit custom address, or even a hacked email address. This one is just an example, of course. And then the CNC server retrieves the email and processes the attachment from the inbox. In the other direction, when the CNC server has a message for one XAGENT module, it sends an email with a message as an attachment to a different inbox, and then mail channel retrieves the email and processes the attachment. So that sounds easy, right? But the thing is, when you are using emails to build a command and control channel, first you need to have a way to distinguish your emails, the CNC emails, from unrelated emails that could be in the inbox, like spam. And secondly, you need to have a way to bypass the spam filters that could be on your way to the inbox on the SMTP servers. To do so, the Sednit developers implemented what they call the P2 scheme, which they describe as a level 2 protocol. And this protocol defines how XAGENT emails are built. And you can see here an email matching the protocol. The subject of the email is the base64 encoding of a value following this format. It begins with a 5-byte random key, then a value called subj token XORed with the key, then the agent ID XORed with the key. And the subj token value here is known by both the CNC server and XAGENT. And that's how they are going to distinguish their emails from unrelated emails. They decode the email subject and check if subj token is here. In practice, in most XAGENT samples, the subj token is a 7-byte value strangely containing the string China. The P2 protocol also defines the body of the email and the attachment name, because remember, the message is in the attachment. And those are simply the base64 encodings of some random values. So that's the P2 scheme. But actually, in our Linux source code, the developers commented out the P2 scheme and replaced it with some hard-coded values. We call it the Georgian protocol, because those values are words in the Georgian language. So the email of a subject is set to Piradi numeri, which refers to a Georgian national ID number, while the body of the email is set to Gamarjoba, which means hello in Georgian, and the attachment name starts with detal uri, which means detail in Georgian, followed by a timestamp. So those values were probably chosen to not attract attention in a hacked in a Georgian infrastructure, or maybe in a hacked Georgian inbox. So, that being said, to conclude on XAGENT, I just want to say a few words on their CNC infrastructure, because once again, we got access to some source code. The source code in question was left in an open directory on the Sednit server, which was for some reason indexed by Google. So by doing some search queries for the P2 scheme I just described, we found it. So the source code is actually a proxy server for a backend CNC server of XAGENT. As you can see from the files, it has been developed in Python, and it was used between April and June 2015, which we know because there are some log files with timestamp inside. The code contains around 12K lines of code because it's actually more than a simple relay of communication. What it does is translating the email protocol, the P2 scheme I just described, from XAGENT infected computers into HTTP requests for the backend CNC server. And those HTTP requests followed another protocol they call the P3 protocol, the level 3 protocol. And by the way, we believe they use the exact same kind of setup for XAGENT using HTTP channel rather than mail channel. So that being said, enough with XAGENT. Let's go back to the chain of events. Day 1, after the initial infection, Sedroco was deployed. Then 4 hours later, XAGENT was deployed. So at this point, Sednit got their 2 spying backdoors on Serge computer, such that if one of them is detected, they don't lose the access to the computers. The next days are going to be about information exfiltration and lateral movements in Serge network. So during the next 3 days, first, Sednit is going to drop some password extractor tools. And very often, they use a set of tools called Security Exploded, which are freely available on the internet. Those tools are able to extract passwords from a variety of software, including browsers and email clients. The thing is that they are well known, so usually detected by antivirus software as hacking tool or something. So Sednit developed their own set of tools. They're custom tools to extract passwords, and in particular, there is one for Windows Live Mail passwords that is dropped on Serge computer. And this particular binary is compiled specifically for Serge, as it searches for the password in a path that exists on Serge computer. Of course, the operators also want to extract Windows password from Serge computer. For that, they got a custom tools to dump the Windows password from registry hives. And of course, without surprise, they use Mimikatz a lot. Very often, the output of Mimikatz used by Sednit is put in a file named p.log. And all these tools may be deployed with local privilege escalation exploits, depending on the target. Serge also meets the screenshotter, which is a custom Sednit tool to take screenshots on the computer. When it is executed, it takes 15 screenshots in rapid succession each time the mouse moves, and it does that 50 times in a row. And finally, Serge meets Xtunnel, which is a custom network proxy tool to contact machines normally unreachable from the internet, using the infected computer as a pivot. Xtunnel appeared in May 2013, and it is still in use. So how does it work? Here is the initial situation. We got the Sednit CNC server on internet. We got Serge computer in its organization network. It's infected with Xtunnel. Computer A and computer B are in the same network than Serge computer. They are not under the control of Sednit, and they are not reachable from internet, but they are reachable from Serge computer. So the first thing that Xtunnel does is an encryption handshake with its CNC server, and the purpose of the handshake is to share an RC4 key to encrypt the communications between the two of them. To do so, both Xtunnel and the CNC server have a copy of a big table filled with random-looking values. Let's name it T. And then Xtunnel randomly picks an offset O in the table T. And the 32-byte row starting at this offset in the table is the RC4 key that Xtunnel wants to share with the CNC server. But of course, it does not send the key itself, but the offset in the table, and also a proof that Xtunnel really knows the table T. And the proof is another row of T located at a fixed offset and encrypted with a chosen key. So then the CNC server checks the proof, and if it's correct, that is the decrypted value is the expected one, it answers OK and sets its own key to the 32-byte value starting at the offset O. So at this point, all the data exchanged between Xtunnel and the CNC server will be RC4 encrypted with a chosen key. Notice that sending the offset and not the key, of course, prevents decryption of the traffic by eavesdroppers. Starting in 2014, the encrypted link was encapsulated into TLS, which is not a bad idea, except that Xtunnel does not verify the certificate given by the CNC server. So now the next step, once this encrypted link has been established, the CNC server can order Xtunnel to open a tunnel with a target computer using its IP address or domain name plus a TCP port number. And then Xtunnel opens a TCP connection with a target computer, let's say computer A, and it will start relaying all the data between computer A and the CNC server in both directions. Notice that the link between Xtunnel and computer A is not encrypted, and any kind of TCP data can be forwarded in the tunnel. We don't know exactly what kind of traffic they send to the tunnel in practice, But it has been reported that this tool is often used with PSExec or PSExec-like tools, PSExec being a sysinternal tool to execute commands on a remote Windows system without having an agent running on the system. So finally, each tunnel is identified by an ID, and using this ID, Xtunnel can actually manage several tunnels at the same time. So for example, another tunnel with a different ID can be opened with computer B, and Xtunnel will take care of routing the traffic into the correct tunnel. Interestingly, starting in July 2015, Xtunnel code was obfuscated, and Xtunnel is, as far as we know, the only Sednit component whose code was obfuscated. July 2015 is 2 months after the attack of Sednit against the German parliament, der Bundestag, where Xtunnel was found and then publicly exposed. So probably what happened is that the detection ratios of Xtunnel increased a lot after the exposure, and they decided to apply some obfuscation to make detection harder. The obfuscation in question is a mix of classic techniques like junk code insertion and opaque predicates. To give you an idea, here is the control flow graph of a small Xtunnel function before the obfuscation and then after the obfuscation. So by the way, if you are building some automatic disobfuscation tool, Xtunnel might be a good toy example because we got samples unobfuscated and then obfuscated with the exact same behavior. And we don't know which tool they used to implement the obfuscation, but knowing Sednit, it may be something completely custom. So enough with Xtunnel. Let's go back to a chain of events. We just had 3 days of information exfiltration and lateral movements. The last action from the operators during this first week will be to set up an additional persistence method on Serge computer for long-term monitoring. So Friday, around 11 a.m., this long-term persistence consists in a special XAGENT binary that is copied in the Microsoft Office folder under the name msi.dll. And this copy operation is done by another binary dropped on the machine. This binary needs to have administrative rights in order to write into the Microsoft Office folder. So for that, they use a local privilege escalation exploit, and then the binary copies the XAGENT msi.dll into the Microsoft Office folder. To understand what happened next, first you need to know that there is a legitimate Windows DLL named msi.dll stored in System32 and used in particular by Office applications. And also you need to know that the XAGENT msi.dll export the exact same function names than the legitimate msi.dll. So you have guessed what happened next. Each time Serge starts an Office application, the XAGENT msi.dll is loaded because it is in the local Office folder and thus it is found before the System32 version. Then it loads the legitimate DLL from System32, fills its own export table with the addresses of a function in the legitimate DLL, such that any call to XAGENT export actually goes to the legitimate one, and the application works normally, and then starts a malicious logic. So it's a simple search order hijacking based on the fact they can write into the Microsoft Office folder. And so, by the way, we have recently seen the same technique used with an XAGENT named linkinfo.dll and dropped in the Windows folder. So that concludes the story of Serge, this textbook case of what happens to Sednit targets during the first days of infection. And now for something quite different, Mr. Jessy.
So now that we have a pretty good overview of what the Sednit ecosystem looks like, I want to talk about a weird case we had last year. In September 2015, we just received an unusual sample, and it was a dropper previously used by Sednit, and it was showing this document as a decoy. As you can see, it's a legitimate invitation for a geopolitics conference happening in November 2015, and it is actually publicly available on the internet. So the payload didn't look like anything related to Sednit so far, and we decided to take a look at it then, hoping for something cool, but sadly, it was just a downloader. Even worse, it was written in Delphi. And since we are good at naming things too, we named it downdelph. But the workflow is pretty simple. First, the payload will download a configuration file on the internet, and then, based on this configuration, it will download and execute another payload. Also, the persistence method used is a very original one, the good old run registry key. So nothing really exciting so far, but it looked like it has never been documented yet. So we started digging for more samples. And we found another down-delve deployment, this time happening in 2013. And this graph described the deployment at the time. As you can see, down-delve came embedded in the same dropper, but this time with a small helper and a Bootkit installer. So down-delve also came with a Bootkit. And even if this Bootkit only infects BIOS-based systems, it has the ability to infect multiple versions of Windows running on an x86 CPU on both 32 and 64-bit architecture. So finally, we do believe this Bootkit has never been documented to the best of our knowledge. So down-delve started to become more and more interesting at this point. And let's have a look at the installation process of this Bootkit. So now, here you have the first sector of your hard drive. Before infection, you have the original MBR located in the first sector. And here is what the same hard drive looks like after infection. So in the first sector, you will have the malicious MBR. And then you will have on the second sector the original MBR saved and XOR with a 1-byte key. And after that, starting from the third sector, you will have the core of the Bootkit code XORed with the same 1-byte key. And after that, you will have a RC4 encrypted driver XORed with the same 1-byte key. Also, the installer will hide two DLL in the registry, but I will talk about them later. So let's describe a very simplified version of the Windows 7 64-bit boot process. So first, the original MBR will be executed, and it will look for a bootable partition. Then when the partition is found, bootmgr will be executed, and it will switch to protected mode, and then it will load Winload.exe. After that, Winload.exe will do some basic integrity checking on the kernel, and then it will load the kernel. The kernel will load its basic drivers, and then the system will start. And now, let's have a look at the Bootkit workflow. So first, the malicious MBR will be executed. And in a very classic way, it will first hook the interrupt OX13, and this interrupt handles all low-level read-write operation on the disk. And by doing that, the Bootkit will be able to intercept every byte read from the disk. And thanks to that, the Bootkit will search the memory for some very specific bytes in order to patch them. Those bytes belong to bootmgr, which is the next step in the boot chain. So at this point, bootmgr is patched, and the Bootkit will take back the control of the execution. So it will search the memory for some other specific bytes. This time, they belong to the function OSL arc transfer to kernel, and this function is located in Winload.exe, which is the next step in the boot chain at this moment. And like the name suggests, this function we call the kernel entry point. So Winload will be patched, and the Bootkit will take again the control of the execution right before the kernel is executed. So now, at this point, we need to understand that the kernel will be mapped into the memory, and all the integrity checks are already performed. So what the Bootkit do now is it will locate one function called mmmap IO space, and it will save some code in the ACPI resource section, ACPI driver resource section. It will also make this section executable. And then it will hook the original entry point of the ACPI driver. Also, to do that, when ACPI will be loaded, we need to understand that the Bootkit physical address won't be accessible anymore. So the Bootkit needs to save all those addresses somewhere, and it will save them in the kernel header. So you can see on the picture, you have the Bootkit physical address here. You also have the address of the function mmmap IO space. It just retrieved. And also you have the original opcode of the ACPI driver entry point. So now ACPI is patched. The driver will be loaded during kernel initialization, and the hook will be executed. So the code hidden in the resource section will first write back the original opcodes on the ACPI driver entry point. Then it will map the Bootkit physical address into the virtual address space with the function mmmap IO space it just retrieved before. And after that, it will be able to finally decrypt the hidden driver. So now, there is three components involved at this point. First, the Bootkit driver will decrypt the first DLL hidden in the registry. This DLL is called by the developer the user mode component of this Bootkit, and it will be manually mapped into the Explorer.exe process memory. And then this user mode component will decrypt another DLL. This time it's downdelf, and it will just load it into Explorer 2. But something was odd with this workflow. They used 2 DLL instead of directly injecting downdelf in the Explorer.exe process memory. And we don't think downdelf actually fits with this Bootkit. And we have found more other evidences that downdelf was not intended to be used with this Bootkit at first. More precisely, first, when injecting downdelf, it set this exported variable to true, but this variable it doesn't exist in any known sample of downdelf, so we believe that downdelf wasn't the original payload of this Bootkit. And also, we believe that this Bootkit, or at least its driver, is connected to the Black Energy malware. Because we have found several shared features between the two families. Like when the user mode component is manually mapped into Explorer's memory, there will be a bunch of relocation fixing and some other things, and all this code is shared between the downdelf samples and the Black Energy samples. And also, to inject the user mode component into Explorer, it will rely on 3 exports, respectively entry, EP data, and dummy. And those 3 exports are shared. You can find them in the Black Energy samples and in the downdelf samples, and they are used in the exact same way. So this might indicate that the developer have access to the Black Energy source code too. But enough with this Bootkit now. Let's go back to downdelf. We looked for some more samples, and we found another deployment, this time in 2014, and downdelf came with a kernel mode rootkit. So at this point, downdelf was definitely more interesting than we thought. And let's quickly talk about this rootkit. So its main purpose is to ensure downdelf persistence on the system, and to do so, it will just inject the DLL downdelf in the Explorer.exe once again, this time using the APC mechanism. And also, it will hide everything related to downdelf to the user and the system, so you can see any file, registry key, or folder on the disk. Thanks to the developers, they just left all kinds of debugging information in the samples. So here is the exact output during the driver loading. And you can see on the picture the files, the registry keys, and the folder to hide, as well as the DLL path the path of the DLL to inject. So we have found 2 implementations of this rootkit. The first one was targeting Windows XP computers, and it was just doing some basic SSDT hooking, while the other one was a Minifilter driver targeting this time more recent version of Windows, and it is based on an open source example made by Microsoft. So let's have a quick look at one of the functionalities of this rootkit. I won't go too deep into the Minifilter's details. I just want to give an example of the rootkit capabilities. So every time a directory or a file will be accessed by an application, this code will be executed. And first, the rootkit will query the file name. Then it will check if the file name or the path matches one of the rules we've seen before. And then if it matches, it will just return the status not found to the application, so the application doesn't know the file exists at this point. And once again, we believe this rootkit has never been publicly documented. And we also found a 64-bit sample of this rootkit, but sadly, we are missing the dropper, so we don't really know how it manages to bypass the driver signing policy. And interestingly, it looks like this sample was targeting a computer running Kaspersky Internet Security. So to summarize, we found only a few samples of downdelf. It was used during the past 3 years, and this is not a lot of samples, so they were probably very careful with it, and they probably used it to target some specific victims. The CNC servers of downdelf was active during the past 2 years. This is quite a long time. It went under the radar. And they used the Bootkit working on Windows XP and Windows 7. They also used the rootkit working on the same version of the operating system. So in short, they work very hard on the persistence methods, which is unusual in such cases. So why did they work so hard to hide such a crappy component? And also, none of them were publicly documented. And to finalize, we know that Dandelf was used in the past to download XAGENT as SEDRECO we mentioned earlier.
So it's now time to conclude with some speculative mumblings, because after looking at so many Sednit binaries over the last 2 years, the temptation is big to try to draw some general conclusions. And I'm not talking about attribution, I'm talking about their software, the way they work. And in particular, there is a question we are often arguing about between us. As we try to show in this presentation, the diversity of Sednit software is quite impressive. If you think about it, there is a Delphi downloader, a Windows Bootkit, a modular C++ backdoor, an exploit kit, an infrastructure with a bunch of custom exploits, and the list goes on. And this diversity is, of course, good for them, because it makes detection and tracking harder for the defenders. So the question is, how did they come up with such vast software ecosystem? And did they develop themselves? Did they outsource the development? So we have a few hints regarding these questions. First, Sednit binaries are often compiled specifically for a target and after the target has been infected. And the perfect basic example of that is this XAGENT sample containing the login and passwords of employees of the Ministry of Internal Affairs of Georgia, used by the mail channel of XAGENT. And so this sample was made specifically to be run inside this organization. More generally, Sednit malware are in constant evolution, and in particular, Xtunnel, SEDUPLOADER, XAGENT, they change a lot since their first version. In other words, the developers are part of the team. They are not outsiders paid for a one-time job. Also, among the variety of Sednit software, there are some shared techniques, like building RC4 keys as the concatenation of hard-coded and randomly generated values, or using hard-coded tokens in network messages. These are just 2 examples of techniques present in several Sednit software that are developed in different languages. So it's not copy-pasted code, it's the re-implementation of the same idea. So this may indicate that the same developers are behind all this software. Another remark on the development process of Sednit is that Sednit software contains some basic programming mistakes. There is one in the Linux XAGENT code where a thread handle named handle get packet is terminated using the API pthread exit, but it should be handle send packet, as you can see from the condition before and from the commented Windows code. So it's a wrong copy-paste in the Linux version. Or this one in Xtunnel, where a report message is built for the CNC server when a tunnel has been opened with a target computer. So the IP address of the target computer and the port number are written in a 6-byte buffer, except that the memory pointer is not incremented between the 2 writes, and thus the port overwrites the first 2 bytes of the IP address. So we can assume the CNC server does not even check the report, and that's how the mistake gone unnoticed. So these are just 2 quick examples of basic mistake you can find in Sednit code. There are more. So clearly the developers do not have a code review process, and overall Sednit code often feels really hackish. On the same idea, Sednit software seems sometimes inspired by classic crimeware. For example, SEDUPLOADER reused persistence methods that were first found in crimeware and shares parts of its code with the Calvet malware. Also, as Jessy explained, the Dandelf Bootkit code bears some similarities with Black Energy code. So we may be tempted to conclude that the developers are connected in some way with some traditional crimeware community. Finally, the exploit kit developers use funny names like Frodo for HTML tags or LOL, and also Messi.Leonel for a binary to download from an exploit. And in case you don't know, Lionel Messi is a famous soccer player. So we can guess that if they are able to use those names in a production exploit kit, they are not working in a very formal environment, to say the least. So to summarize this speculation, we believe that the Sednit Group has some in-house skilled developers working with little or no supervision, and those guys have ties with crimeware underground. And we would be very happy to discuss about it if you disagree. Enough speculation, time to conclude. So Sednit activity increased a lot during the last 2 years. They are doing targeted attacks, but they got a lot of targets. By the way, if you have heard about the DNC hack in the US last week, Sednit was supposedly involved. And also, their toolkit is in constant evolution, so there is certainly more fun to come for malware researchers. Thank you very much for your attention. If you have any questions, feel free to contact us, and there will be a white paper published with all this content and more, hopefully during the summer. So thank you, guys. If you have any questions. Thanks. Oh. You mean the timeline of Serge, the action? So it's based on several real cases we investigated. So where we did some forensic on some computers that were attacked by Sednit. And so we had the timings precisely of what happened during the attacks, and we kind of merged several cases to build this ideal visibility cases. But maybe we should mention that we don't have visibility on their real traffic, the traffic they exchange between the malware and the Sednit CNC server. So what we had is binaries drop at certain times on the computer, and we merge the cases. Thanks.